All right, so now today we're going to talk about, thank you. Today we're going to talk about expressing concentration. This, in and of itself, this is not a hard concept. Add to this the fact that on the multiple choice, which is when these questions are typically asked, you don't get a calculator and you also don't get an equation sheet. And then it becomes a little bit more difficult because now you have to actually remember how to calculate all of these. But they're not that bad. I think most of them make sense. So, well, okay. First of all, we have already talked about a major way of expressing the concentration of a solution. What's the main way we've talked about so far? Molarity, right? Okay, moles per liter. That's the main way we've talked about concentration. So we're just going to talk about some different ways of expressing it that you might see in another chemistry class in college or on the AP exam. So the first one is a mass percentage. Now we've kind of talked about mass percentages too. What was the context that we've talked about mass percentages? You guys remember? It's been a long time, actually. You'd have to think way back to the beginning of honors chemistry when we were doing, like when I was giving you a formula like CaCO3, and I wanted to know the percent of calcium in CaCO3. Do you guys remember doing that? And then you just use the molar mass from the periodic table. Okay, 40 grams of calcium over, however much there is in that whole compound. So that's, you've already kind of learned that way of expressing concentration. But now we're talking about it in terms of something that's dissolved in a solution. Okay, so you just take the mass of whatever it is in your solution, the mass of Kool-Aid in your solution, divided by the total mass of your solution, and that's going to be the mass percentage. Okay, so pretty straightforward. Another way that's kind of related to that, but it's more by amount than it is by mass. Wait a second. No, I'm sorry, this still is a mass percentage. I apologize. Parts per million might make you think more like we're counting the individual pieces of it. Sometimes concentrations in solutions are very, 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 very small. And so instead of writing a really small number like this has a mass percentage of 0.00012 or something like that, if we multiply that by 10 to the 6th, that gives us parts per million. Okay, so you just move the decimal over 6 places. Now, why would that be useful? Or in what scenario would we need to know the concentration of something when it's in parts per million? You guys can think of a good example of when that might be useful. Let's say I want to know how much mercury is in the water I'm drinking, or how much lead, or or any sort of toxin. Okay, most of these things that can be in our water supplies, the United States has sort of defined, or not even necessarily the United States in some of these, but the scientific community has defined a certain concentration that is allowable in our drinking water, and you don't want it to go above that concentration, right? That's why pregnant women are not allowed to eat big fish. Okay, do you guys learn about biological magnification in biology? Okay, all right. So the idea of biological magnification is if there's a little bit of mercury in the water, then all of these fish are sort of all these tiny little fish are sort of taking in some of that mercury, and it's getting stored in the fat inside their bodies. Okay? Well, then bigger fish come and eat the smaller fish, and they're eating a bunch of those smaller fish, so they get all of the mercury that's being stored in the fat of those smaller fish, and that gets stored in the fat in their bodies. Okay? And so now the bigger fish has a little more mercury than the smaller fish did. Okay, and then an even bigger fish comes along and eats that, and now this thing, the higher up the food chain it goes, the higher the concentration of mercury. So you don't want to eat swordfish when you're pregnant because that swordfish probably tends to have a higher concentration of mercury in its body or in its fat. than a small fish. So tuna, I think they usually tell pregnant women tuna's okay, swordfish not. Okay, because tuna are smaller, swordfish are bigger, that sort of thing. Okay, so parts per million, a little bit of a tangent there, but at least some things in this class are practical in everyday life, right? So this is where this gets used. Sometimes the concentrations are so small, we would even express them in parts per billion. Okay. And so, I mean, we're talking about a very, very, very small concentration. But there are some things, even if they're present in a concentration of parts per billion, they can kill you. Right? So, I'll bet, I don't know for sure, but I'll bet in forensics they talk about parts per million and parts per billion when they're talking about poisons and that sort of thing. I would assume they have a section on poisoning and how to identify the different poisons that might have killed somebody. Okay, so that's another couple. These are basically, and what I want you to understand here, these are basically mass percentages, but they are expressed. I mean, if you have a really, really, really small percentage, that's when the parts per million or parts per billion might be useful. Okay. So, do we have an example of that? Yeah, we do. Okay. So, solution is made by dissolving 13.5 grams of glucose in 0.1 kilogram of water. What is the mass percentage of the solute in this solution? Okay, so this one was not designed for you to do without your calculator. The ones that you get on the multiple choice typically will be. So this one, I mean, you find to use a calculator on this one. So the mass percentage, we're just taking the part divided by the whole, right? What's the mass of our part here? 13.5. 13.5 grams of the glucose. You don't necessarily have to label this as glucose here. Divided by the mass of the solution. Okay? So what's the mass of the solution here? Okay? Now you have to be careful here. Alright? Remember the law of conservation of mass. When I put glucose into water and it dissolves, does the mass of that glucose go away? No, so that's gonna count as part of the total mass of our solution, right? Okay, so we're talking 113.5, if I'm doing my math right, grams of the solution. And then you multiply that by 100. Actually, you might be able to do this one in your head. No, I guess it doesn't work out. I thought maybe the numbers would work out nice, but they don't really. So, I'm getting about 12% on that one. How many sig figs do we have? 3? So 11.9%. Is that what you guys are getting? Okay. 11.9%. Okay. So that's the percentage. And really, the one big thing that could trip you up on these is just forgetting to add the solute into the mass of the solution as well. Okay. All right. A 2.5 gram sample of groundwater is found to contain 5.4. You guys remember what that little symbol stands for? That is the micro symbol. So that's micrograms. Okay. There are 1,000,000 micrograms in a gram. All right. So it contains 5.4 micrograms of zinc. What's the concentration in parts per million? Okay, so we've got a 2.5 gram sample of groundwater, and we've got 5.4 micrograms of zinc. So if we go back to the, whoops, way too far. Parts per million here, which is what they want. You take the mass of whatever we're looking at divided by the total mass of the solution, and then you just multiply it by 10 to the 6th instead of multiplying by 100, and that'll give you parts per million. Okay? So it's very much like the mass calculation, mass percentage calculation. So we've got 5.4, and I'm going to have to change these so that they're in the same units, right? So maybe we can actually talk about doing that first before we do our calculation here. In 1 gram, there's 1,000,000 micrograms. 1 times 10 to the 6th, basically. So actually, I mean, if you do this all in one step, it might be a little easier, but we'll do it this way just so you can see what's going on here. But we're essentially going to cancel out that 1 times 10 to the 6th when we multiply by 1 times 10 to the 6th at the end. So that's 5.4 times 10 to the 6th, 10 to the negative 6, sorry, grams, okay? So that's our zinc, okay? So we take 5.4 times 10 to the negative 6th grams divided by the total mass of the solution, okay? What's the total mass of the solution? Well, on this one, I mean, if you take, on your calculator, if you take 2.5 plus 5.4 times 10 to the negative 6th, it's 2.50000054. So to our number of sig figs, yes, it is just 2.5, okay? But again, you have to add these two numbers normally to get your mass percentage, okay? Oh, I see what you're saying. Okay, because it's a 2.5 gram sample of groundwater. Yeah, I guess you're right on that one. Yep, that makes sense. Good job. Very good. So, yeah, so this is already our sample of groundwater, so it already includes that in it, and then when you separate out the zinc, then that's how much of the zinc you have. Whoops, not times 100. We're doing parts per million here, so we multiply that by 10 to the 6th, okay? So then when you do that, you should get 21.6, I think. Is that what you guys are getting? 2.16. Well, I may be making a lot of mistakes this morning. 5.4 times 10 to the negative 6th divided by 2.5. It's giving me 2.16 times 10 to the negative 6th. And then times... Yep. I punched in my calculator wrong. Good job. 2.16 parts per million. It's a good thing I'm doing this in front of people this morning. I would have made 2 mistakes already on my video. Alright, so 2.16 parts per million. And what I did, I put in 10E6 on my calculator, which I told you guys not to do that last year, didn't I? You put 1E6 because that's the same thing as 1 times 10 to the 6, which is what you want to put. Getting interesting announcements this morning. Okay, mole fraction. This one we don't need to talk about a whole lot because we just talked about this in the last unit that we covered in the gas laws, right? But you can find a mole fraction with solutions just like you can with gases. All right, it's just the moles of whatever you're looking at divided by the total moles in the solution. So I don't think we need to talk too much about that, but I'm just going to mention that as a way of expressing concentration. I guess I gave you guys blanks on this one. Huh. Okay. I forgot that I did that. Oh, I remember why I did that. Because I was being lazy and I didn't want to actually like put in the whole... It takes a long time to put that into Microsoft Word, type it all in. So I'm just going to let you write it. Okay. Now here's what you have to be careful of. You need to pay close attention to this because sometimes they will ask you, let's say that you've got sodium chloride dissolved in water, something like that. They might ask you, what is the mole fraction of the water? Okay? Which is kind of weird. So you have to just watch out for that. Make sure, you know, it's going to be very natural for you to want to calculate the mole fraction of the salt in the water. But sometimes they might ask you for the mole fraction of the water in the saltwater solution. Okay? So just pay attention to what they're asking you for. Okay, molarity, we don't need to talk about that one too much either because we talked about that one in chapter 4 in the book when we talked about aqueous solutions. But here's the problem, the one main problem with molarity as a measure of concentration. It's temperature dependent, okay? And so you change the temperature, you change your concentration. Now the reason for that is because volume is a little bit temperature dependent, right? Now, we're not going to change the volume of a liquid a whole lot when we change the temperature, but we will change it a little bit, okay? So you can actually If you heat something up too much, you can't actually change the concentration of it because now the volume of the solution is going to be a little bit higher than it was before. Does that make sense? So molarity, I mean, it's a pretty good measure of concentration. But if you want something that's not going to change dependent on temperature, then you might want something else, like some of the other methods we've talked about, okay? Now, molality is a very common one that is not temperature dependent because it has to do with the moles of the solute and the kilograms of the solvent, okay? And we know that moles and mass, neither one of those things change when you change temperature. The amount of the solute that you have in there is not going to change with temperature. So this one's temperature independent. And you have at least a couple of questions on your AP packet that ask basically that. It gives you a list of different ways of expressing concentration. It says which of these is temperature dependent, okay? And then you would pick molarity, okay? All right. So another sample problem here. Are we getting close to the end? Okay. And now we've just got some practice problems, basically. So, are we halfway? Okay. All right. So, are there any other types of concentration to discuss? Oh, okay. There's a discussion of how to get from molarity to molality. I forgot about that. Okay. Thought we were almost done already. So, we've got a solution here. We've got 4.35 grams of glucose, 25 milliliters of water. We want to calculate the molality, okay? So again, remember, and this is one of those things, unfortunately, this one you're probably just going to have to commit to memory because this is one that you're not familiar with. The mass percentage, okay, take the part divided by the whole, right? Parts per million, they usually don't ask you about that one on AP exams. But if you just know that's mass percentage and then you multiply it by a million, then you're good to go on that one. This one, the molality, you're probably just going to have to memorize. Okay, so molality is moles of solute over kilograms of solvent. How many moles of our solute do we have here? How would we even figure that out? Okay. So we need to change this to moles, right? By using the molar mass on the periodic table. I don't remember what that is off the top of my head. I think it's 180. I could be wrong. Yeah, 180. Give or take. It's kind of pathetic I have that memorized, actually. Okay, so 4.35 divided by 180, so we have 0.024 2 moles. Both three sig figs there. Okay, so that's our solute. Then we need kilograms of solvent. What's the solvent? Okay. Kilograms of water. Well, density. There we go. Okay, if you know the density of water is 1 gram per milliliter, then 25 milliliters of water is 25 grams. We're making a little bit of an assumption here, okay? So we've got 25 grams of water, and you can probably do this in your head, but we'll go ahead and work this out just in case you can't. There's 1,000 grams in a kilogram, so we need to divide by 1,000. That's going to give us 0.0250 kilograms. Okay. So now you've got moles of the solute and you've got kilograms of the solvent. Okay, now this one, molality, it's not kilograms of the whole thing. Okay, so you don't have to add the mass of the solute and the solvent together. This is just kilograms of the solvent. Alright? You got to shift your brain out of the mass percentage way of doing things here. So this is going to be 0.0242 divided by 0.0250. That's going to be close to 1, isn't it? 0.968. Is that okay? Oh, it's exactly 0.968. Okay, and that's, we need 3 sig figs, so that works out well. And what are the units here? moles per kilogram. Okay. Now, there's two ways you might see this unit written. Just like molarity can be written as moles per liter or as big M. The other way that you could see this written possibly is, no, you're not going to be able to see this for a second, 0.968 little m, and they usually put it in italics. Okay. So those are your two ways that you might see the unit molality, which, again, very confusing. Big M can stand for molarity. It can also stand for molar mass, depending on whether you're working with gases or solutions. Little m can stand for mass, or it can stand for molality. Okay, so M is just used for way too many things. But okay, so if we have molarity, you can get to molality as long as you know the density of the solution. Okay, which we just used the density to kind of do that, right? And then you can go backwards, you know. If you start with the molality, you can also get to the molarity. So this has nothing to do with what I just said. This is a different kind of practice problem, but this is basically just, okay, let's practice a few of these ways of expressing concentration that we haven't practiced yet. So we've got 36% HCl by mass, and we want to know the mole fraction of the HCl in the solution. Any ideas? Okay. Okay, so let's assume we have, and we did this a little bit last year, right? When we had percentages, let's assume we have 100 grams of solution. Okay. So if we have 100 grams of the overall solution, 36 of those grams is going to be the HCl, right? So we've got, and we want to know the mole fraction here. Okay, so we've got 36 grams of the HCl. And then what's the rest of it? So what is the rest of the solution? HCl is probably dissolved in water. Okay, so the other 64 grams are the water. Now, there's a couple different ways of doing this. You could actually do this all at once in one giant calculation. I'm going to do these two parts separately, and then we'll combine them at the end because I think that's a little bit easier to think about. But if we're gonna find a mole fraction, we need to know the moles of each of our parts, right? And right now we know the mass of each of our parts. So let's change the grams of HCl into moles of HCl. And then we'll change the grams of water into moles of water. This one I know, this one's going to be 36.45 or something like that. Approximately. Okay. Are we alright so far? You guys understand what I'm doing here? Just getting everything to moles because that's what we need in order to do a mole fraction. Okay. So, oops. Oh wow, yeah. 0.9876543 and if you round to how many sig figs, I don't know, like 10 sig figs, then it's 0.987654321. Yeah. I planned that. So really, I mean, for our sig figs here, we only have 2 sig figs, so it'd be 0.99. But you wouldn't necessarily want to round that quite that soon either, so I don't think it's going to make a big difference here. And then 64 divided by 18 is 3.6 moles of H2O. Okay, and then here's where you have to be a little bit careful. This is a mole fraction, which is basically like a percentage, right? We take the moles of our solute divided by the total moles. Okay. Now, here's one example of where I said you need to be a little bit careful. They could have just as easily asked you for the mole fraction of H2O in that solution, right? Then you'd have to put this one on top, 3.6 on top. So just be careful what they're asking you for. But on this one, we're trying to find the mole fraction of the HCl, so it's just 0.99 moles divided by, what's the total number? 4.59? Okay, thank you. 4.59 moles. And don't multiply this one times 100, because it's not a mole percentage, it's just a mole fraction. Nope. Almost put it in wrong on my calculator. So I'm getting like 0.22, is that right? And what are the units for mole fraction? No, it doesn't. You'd want to put the mole fraction in a decimal, which is a little bit confusing, but yeah. This is moles over moles, right? So those cancel. This is a unitless number, okay? But it can happen sometimes. So actually, really, percentage is a unitless number as well, if you think about it. You put the percent at the end, but you're dividing grams by grams when you do the mass percentage, so the same thing happens there. Okay. It's just weird because there's no percent or anything behind it. We're used to at least putting something behind this number, but that's a unitless number. Okay. Now we need to calculate the molality of HCl in the solution. Okay, did we do anything on the first part that might help us with the second part here? We found the moles of HCl, right? Okay, which we found to be 0.99. So we know that at least. And then we need to figure out the kilograms of the solvent, which actually, we assumed that we had a 100-gram sample here, right? So 64 grams of H2O, just change that into kilograms, and then we're good to go. So that should be 0.064 kilograms of H2O. Now HCl, well, maybe I don't want to introduce any more confusion there. You guys okay with H2O being the solvent on this one and HCl being the solute? Okay. Sometimes it's hard to tell. Sometimes the best criteria to use for deciding what's the solute and what's the solvent is, what's that? Well, yeah, I mean, it's weird to think about H2O dissolving in something. So usually if we talk about a solution that has H2O in it, that's going to be the solvent. Okay? But let's say we have a couple of things that it's a little bit tougher to distinguish between. Like maybe I'm talking about ethanol dissolving in carbon tetrachloride. How would you know which one is the solute and which one is the solvent? I don't think I have a problem like this, so I'll go ahead and talk about this. Let's say we have 18 grams of the carbon tetrachloride and what do I want to say here? Like 2 grams of the ethanol. It's supposed to be an E, and that's supposed to be an A. So, which one do you think you would probably call the solute there? What is being dissolved? Probably the ethanol, and the reason is just there's less of it, right? Okay, so I mean that's usually the way we think of it. Now sometimes they might say, you know, 2 grams of ethanol is dissolved in 18 grams of carbon tetrachloride, and then it's pretty obvious which one is a solute and which one is a solvent. Okay, so but that on these types of calculations that can become important. So usually you just want to go by the amount, and that will tell you which one is the solute and the solvent if it's not immediately obvious. And on this one, I think it's pretty obvious. Okay. All right, so we take these divided by each other, and does anyone have that one calculated? 15.5. 15.5 moles per kilogram, or just little m. Okay? That seems like a fairly high concentration, doesn't it? 15.5. I mean, compared to the last molality that we calculated. 36% HCl, that's a good amount. It's fairly concentrated. That'll do some damage. So, That's a decent number there. Okay. Solution contains 5 grams of toluene and 225 grams of benzene, and has a density of 0.876 grams per milliliter. Okay, actually, this is kind of an example of one of those where you might not immediately know what dissolves in what, but what is the solvent here, most likely? Probably the benzene. There's a lot more of it, right? Okay. Now, the solvent doesn't matter so much, but we need to know what the solute is if we're calculating molarity, right? Because molarity is moles of the solute divided by liters of the solution. Okay. Okay. So here's the thing. When you read this problem, you might be initially a little bit confused because we need to find liters of the solution. And it almost seems at first glance that they're giving us the density of the benzene. Is that what they're giving us the density of here? They're actually giving us the density of the entire solution, right? Okay. So where you have to be a little careful here is you actually have to add up these masses first, right? We need to know the total grams of everything we have in this solution before we multiply by the density to find our liters of solution. Does that make sense? It's because it's not just giving us the density of the benzene, it's giving us the density of the toluene and the benzene together. Okay? It's just worded a little bit weird, so you have to be careful with that. So we've got actually 300. Wow, that's my finest math moment right there. 230 grams of the solution, right? And then if we use our density here, this is 0.876 grams in 1 milliliter. That's going to give us our milliliters of solution, and then we can change that. Actually, maybe I just want to do that all in one step here. Go from milliliters to liters. Okay. .26. Let's see here. This is technically 230 grams of solution. When we add those two, it's significant to the ones place. Our students are going to be proud of me right now. Doing my sig figs. So there should be 3 sig figs in our answer here. 0.263 liters of solution. Then we just need to find the moles of our solute, which, again, our solute is the toluene because there's less of it. So 5.0 grams of that. We just need to change that into moles. About 92. And now our students are going to be mad at me because I'm just estimating on my molar mass. 5 divided by 92. 0.054. Okay, so then if we want to find the molarity, we just take the moles of the C7H8 divided by the liters that we found, 0.263, and that's going to give us our molarity of about 0.207. Well, no, I should have rounded this. I did round that one to 2 sig figs, so 0.21 molar. Okay. So again, not super difficult. The main thing that makes these difficult, like I said, and we'll do some practice on this in class, is just not using a calculator and remembering all the formulas that you have to remember. Any questions on this stuff? Like I said, it's pretty straightforward. Okay. We're done for the day. I mean, not for the day. We're done for the part before school starts.